In the last video, we introduced this idea of quadratic approximations, and we found some quadratic approximations, and we got some familiarity with this formula. And in this video, I just want to keep getting us more and more comfortable with this formula and work on constructing some quadratic approximations for some functions. So what I have down here are a few functions, and I want you to pause the video and make some quadratic approximations for these functions at x is equal to 0. And again, this notation here is saying, okay, make a quadratic approximation for these functions at x is equal to 0, and then use those quadratic approximations to approximate values of this function for x values near 0. So why don't you pause the video and give that a try on your own. All right, assuming that you've given it a go, let's begin. So maybe since we want to make some quadratic approximations at x is equal to 0 and use them for x values near 0, we can just get a formula for that situation. So we're interested in for x values near 0, f of x is going to be approximately f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 times x squared. So that's what we find for our quadratic approximation formula for x values near 0. And then all we're going to do is just find these, find f of 0, find the derivative at 0, and find the second derivative at 0. And then we can make quadratic approximations. So maybe it'd be a good idea. Let's, you know what? Let's make a table. So we want to find f of 0, and we want to find our derivative function, and then evaluate it at 0. And then we also want to find our second derivative, and then evaluate it at 0. So all we're going to do is just fill in this table here, and then we'll combine the information and make some quadratic approximations. And again, at any point, if you feel like, okay, I've seen a few examples, why don't you pause the video and try to finish off some of these functions? Okay, so cosine of x, we worked with this guy in the last video, so let's just fill in this table. So cosine of 0 is 1. The derivative of cosine is negative sine of x. Evaluating this at 0 is just 0. Derivative of negative sine of x is negative cosine of x. Evaluating it at 0, we get negative 1. So filling this in, using this formula up here, we have that cosine of x is going to be approximately 1 plus 0x minus 1 over 2. Then we have x squared. And that's what we found. Just clean this up real quick. We have 1 minus x squared over 2. That's what we found in the last video, so we're off to a good start. And now let's work on sine of x. So sine of 0 is just 0. Derivative of sine of x is cosine of x. Evaluating cosine at 0, we find 1. Derivative of cosine is negative sine of x. And then evaluating this at 0, we find this to be 0. And then we find, just using our information here, we find that sine of x is going to be approximately 0 plus 1 times x plus 0 over 2 times x squared. If you want to throw that in there, clean this up, this just is x. And you might be saying, okay, whoa, we're making quadratic approximations. I don't see any quadratic terms in here. And from our formula, you can see why. Our second derivative is 0. But does that mean that this is just a bad approximation, or like why isn't this better? Well, we can maybe look at the graph of sine of x and see that this approximation is still pretty good. So if we just get a nice little rough sketch of sine of x, and mostly we're going to be paying attention to the origin here. So something like that. Okay, I think you get the idea. It's not perfect, just a little rough sketch. And then if we were to graph this, so this is saying y is equal to x. If we were to graph this is going to be a line, and it's going to go through the origin and look something like that. And you can see in approximating sine of x for x values near 0 that this line seems to do a pretty good job. So it is still a pretty good approximation. Now let's move on. Let's talk about e to the x. All right, e to the x, e to the 0 power is 1. Taking the derivative of e to the x is just e to the x. You gotta love it. So again, we get 1, and then e to the x, and then we get 1. All right, filling this in, e to the x is going to be approximately 1 plus 1 times x plus 1/2 times x squared. Cleaning it up maybe just a little bit, 1 plus x squared over 2. All right, moving on, we have 1 plus x to the rth power, That's pretty funny. So evaluating this at 0, 1 to some power is just going to be 1. Taking the derivative by the power rule, we have r times 1 plus x to the r minus 1 power. Evaluating this at 0, again, 1 to some power and then times r, so this is just going to be r. Taking the second derivative, again, power rule, so we have r times r minus 1 times 1 plus x to the r minus 2 power. And again, it's just r times r minus 1 times 1. So we get r times r minus 1. Filling this in, we have 1 plus x to the rth power is going to be approximately 1 plus rx plus r times r minus 1. Here, that's not very legible. Let's go back. R minus 1, there we go, over 2 times x squared. And then lastly, the natural log of 1 plus x. Evaluating that at 0, we get the natural log of 1, which is just 0. Taking the derivative, we have 1 over 1 plus x. Evaluating this at 0, we have 1 over 1, which is just 1. And then taking the derivative of 1 over 1 plus x, I'm just going to rewrite that. I always like to rewrite these with a negative exponent. So 1 plus x to the negative 1 power. Then we use the power rule. So this is negative 1 times 1 plus x to the negative 2 power. And again, the derivative of the inside is just 1. So we're good there. Evaluating this at 0, we are just going to get negative 1 times 1 to some power. So that is negative 1. Filling this in, we find the natural log of 1 plus x is going to be approximately 0 plus 1 times x plus negative 1 over 2 times x squared. Cleaning it up, we get x minus x squared over 2. So hopefully we got some good practice here, and you're starting to feel a little more comfortable with making some quadratic approximations. Maybe you've been wondering, okay, why are we doing these functions here? And what you're going to see in the upcoming videos is that if we know the quadratic approximations for these functions, when we start to get more dressed up versions of these functions, and maybe we take products of some of these functions, that knowing the quadratic approximations of these, we can greatly simplify our calculations of the more dressed up versions that would be harder to make quadratic approximations for had we not known this. So you can see that in the upcoming videos.